right, everybody, I think it's about 4 o'clock. I think I'm gonna go ahead and get started. Welcome to, well, what is our, last regular class of the semester? I forgot to bring my Kleenex box, but probably should have. It's a little bit teary-eyed time for me. I really do enjoy doing this for 15 weeks with you guys, and so I will definitely be missing it very, very soon. So, but yeah, it's definitely been a lot of material. A long semester is a lot to think about, and I'm going to spend most of today talking about the final, making sure everybody feels good about that and is understanding what to expect. But we have one last little piece of new material to go over first, and I'd like to do that first so that then I can be done with that and then spend the rest of the time talking about our exam coming up, as well as the exam that we just took. So the section that I have up here is 9.6, just one quick 35-minute section. We'll be done with this. And this is talking about non-homogeneous, that's the key word here, non-homogeneous linear systems of differential equations. So if you go back and remember, for most of this chapter, we've been looking at x prime equals ax, okay? But I did mention right at the beginning of this chapter that there could be, within this system of differential equations, there could be some terms that do not touch the unknowns, that do not have the unknowns in them or multiplying in them. And I called that the vector B here. So in this one last section, I'm going to talk about what to do when B is not 0, if it's not homogeneous, in other words. Okay, so that's what we're going to go over. I'm going to just explain to you how to solve this. And just as a little bit of a carrot for you, I'm going to promise you that there will be one of these on next week's test. So we're going to practice one now. You're going to do 2 quick practices on the homework. There's one last homework assignment due. And then you will also see one of these in the group work and in the sample final and that kind of place. So by the time we get to next week, I'm hoping everybody will have tried, I don't know, 3 or 4 of these on their own and should feel pretty solid on it. There's only 2 equations that you have to learn for this section, and I will highlight and box them and point them out to you. They're not very hard to learn, but there's just 2 things you have to memorize, and then the rest of it is just going to go on autopilot, okay? So let's just discuss how we're going to solve a non-homogeneous system of differential equations. It's done in 3 steps, which is going to sound very familiar. Let me write down 3 steps to solve for x. Okay, so it's just a 3-step process. These steps are going to sound very familiar to you, okay? Because we've had something like this before. The first step is to solve the corresponding homogeneous system. This is going to be x prime equals a times x. So in other words, in the first step, we're just going to ignore the b that's on the right-hand side for what is called the complementary function. So that's a word that we've also heard before. The complementary function is x sub c of t. So we solve the corresponding homogeneous system for the complementary function. All right, so we know how to do this already. We talked about doing it if the matrix is defective. We talked about doing it if the matrix is non-defective, whether it's real eigenvalues, complex eigenvalues. Right? We did all of this before. Okay, so that's kind of an old process right there. Step 2, guys, is that we have to find one particular solution, and I'm going to call this one x sub p of t. one particular solution to x prime equals a times x plus b. And it is done via, how do we find one particular solution? It is done by a technique which you guys know well. It is called variation of parameters. So I'll come back in a moment. I'm going to explain what that looks like in this context. Okay, so we have to find one particular solution. Let's just say here C below. So in a moment below, I'll explain that step. Okay, and then can somebody tell me what step 3 is going to be? Add them together, right? So for the general solution, you got it. The general solution is going to be x of t equals x sub c of t plus x sub p of t. And as always, you are welcome to just write this down for step 3. If you don't want to recopy, if you're working one of these out and you don't want to recopy everything from the complementary function and the particular solution, you can just write this down and that will remind me to that you know how to do that part. And I graded your exams that way. If somebody didn't have anything on their paper except basically the step 3, I gave them a couple points just for that. Okay, so I will do that again. So just writing that down is step 3. That part's pretty easy. Okay, so let's talk about step 2. So step 2 is the new part. This is where we discuss what's really going on that's new here. I first want to write down how the complementary function will have looked. So in the first step, I would have figured out the complementary function. So let's just say from step 1, right, x sub c of t, as you guys know, because you've done step 1 before, it's just a linear combination. It'd be like c1 times x1 of t plus c2 times x2 of t and dot 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 plus cn times xn of t. We kind of already know that that's how we could write it. I actually want to write that in a slightly different way. I'm going to write it in a more sort of matrix formatted approach if I could. And the way that's going to work, guys, is I'm actually going to put these x's into the columns of a matrix here. And so I'm going to, each of those solutions from step 1 can be written down as a column, and it is going to get multiplied on the right by C1, C2, and dot, dot, dot down to Cn. Now, this is literally a matrix multiplication. So just to remind you, of course, we would do dot products to calculate this matrix multiplication. If you did that here, guys, if you go across the rows of the matrix on the left and down this column, the C1 is only going to touch the entries from X1, right? Like this, right? That's how you do it. So C2 will only touch X2. C3 only touches X3. Xn and Cn are lined up. So it exactly matches what we have above it. C1 multiplies X1. C2 multiplies X2. C3 multiplies X3, and so on. This is literally just a way of rewriting what's on the line above. Okay, and we can even do one more step and just write this as capital X, and it is a function of t, so let me put that t there, times this vector c, where, so I'm going to use a capital X for that matrix, guys. Capital X is just the matrix whose columns are these solutions, x1, x2, and dot, dot, dot up to xn. Capital X is a fundamental matrix. So it's called the fundamental matrix. If you ever hear anybody talk about the fundamental matrix for a system, That's what they're talking about. You're just laying these vector functions into the columns of this matrix. By the way, these columns, they're all linearly independent. After all, the x1, x2, x3, those are a basis for the solutions to the homogeneous system. And if they're a basis, then when you write them down, they are Li. And if the columns of a matrix are Li, then that matrix is actually invertible. So let's just add that here. Let's just say which is invertible. I'm just going to keep going. Let's come up here. Since its columns are Li. So the columns of that matrix are the linearly independent solutions from step one. And so you got a matrix here with Li columns, so it's an invertible matrix. Far so good? Well, now we come to variation of parameters. How we actually do the step two. Find one particular solution by using what's called variation of parameters. I just want to scribble over here. You don't need to write this down, but I want to remind you how this looked in chapter 8. In chapter 8, you guys will remember that we had a complementary function, and it looked like, C1 times Y1 plus C2 times Y2. And you might remember that when we went to the variation of parameters method, what we had to do with that complementary function is we had to vary the parameters C1 and C2 by rewriting them as U1 and U2, right? So do you guys remember that? So this was U1 times Y1 plus U2 times Y2. That was how the variation of parameters solution would have looked. So you know what I'm going to do is I'm going to mimic that exact thing here. If my complementary function, let's just actually come back here and box this right here. If my complementary function looks like capital X times C, then what we're going to do here for the particular solution is now we use a trial solution. I'm going to write it for you here, guys. The particular solution, X of P of T. By the way, this is the first of the two. I said there's two equations today that are new that you have to memorize. This is the first one. And what it is we're going to do exactly what we did over here, which is we're going to change the C1 and C2 to U1 and U2. In other words, we're going to change the C vector to U vector. Okay, so we're exactly mimicking this approach. And here, this is where U is to be determined. It's the usual thing, guys. We're taking a guess. A trial solution is like a guess. We're going to hope that we can get X of P of that form to actually work. Okay. Everybody with me so far? Okay, I'm just deriving this for you. At the end of the day, you're only going to need to know these two equations and you'll be able to do step two. So it won't be anything too crazy. Okay, so how do we actually figure out how to make this trial solution work? We do what we've always done, which is we take our trial solution and we plug it back into our problem on the left side and on the right side, and we match it up, line things up and see, okay, what would U have to be in order for it to work, right? So exactly the game we're going to play. So that's how we're going to do it. Before we do that, though, I'm going to make a quick little note here. I meant to make this note a little bit earlier, but I'm going to make it right now. I just want to look at what happens, because in a minute when I plug this trial solution into my linear system there, this is going to show up. At some point, we're going to see A times capital X. And I would just like to show you what that is. If we do A times capital X, this is kind of an interesting little note. This is just A times the matrix, this is the fundamental matrix whose columns are x1, x2, and so on up to xn. And so what you're doing here, guys, is you're doing a matrix multiplication. Both of these matrices are n by n. And you're going to do dot products across the rows of A down each of these columns. And how will that end up looking? Well, the first column of the product will just be whatever A is times x1. And the second column will just be A times x2. And so on and so on. The last column will be A times xn. I am curious, what is A times x1? Angel? X1 prime. Guys, the x1, very good. The x1 was a solution to this, wasn't it? So AX1 is x1 prime. AX2 is x2 prime. And so on and so on, right? So that's exactly right. This is just x1 prime. Second column is x2 prime, and dot, dot, dot. Last column is xn prime. And I might have been teaching for 20-something years. I still don't quite do things right. I have barely enough room on the bottom of my board here, but can everybody squeeze in? You notice what I've done here is I've simply taken the derivative of everything. Can I just call that capital X prime? That's what I'm trying to do. Capital X is just this matrix here. If you put a derivative on it, you literally are taking the derivative of every single entry of every single column. So the capital X prime is just the matrix whose columns are the derivatives of those x's. So this was my note. All I care about, A times X equals X prime. Now let's plug in our trial solution. So plug trial solution into X prime equals A times X plus B. Okay, so on the left side, I will have X sub P prime. On the right side, I'll have A times X sub P plus B. So that's what you would get if you just plug that in on both the left and the right. X sub P prime equals A times X sub P plus B. So X sub P prime, that would be the derivative of this. Okay, so let's just write that. This is X times U prime. And on the right, I have A times X times U, and then plus B. Everybody with me? We're already almost done. Yes. On the left side, I have the derivative of a product. We all know the product rule, right? The product rule tells me that this is going to be X prime times U plus X times U prime. And on the right side, I have A times X times U plus B. I'm just leaving the right-hand side the same for a moment. And I'm wondering if anybody can help me to simplify that. Let me make sure I'm not standing in the way. Sorry? I think I heard you say it. Nope. My ears are going. So I just proved this. A times X, it's the same thing as X prime. What do I have over here? Oh, here's an X prime U, and here's a AX U. Right, the left side has X prime U, the right side has AX U. But wait a minute, AX is the same as X prime. Guys, these two terms, they cancel completely. They cancel completely. Because A times X is the same as X prime. They cancel completely. And so guess what, guys? All we're left with is X times U prime equals B. My goal is to solve for U. In order to solve for u, I need to get it by itself. The first problem with that is I have an x in the way. But we just said over here that capital X was invertible. I have an inverse. And so if I have an inverse, guys, we can use that here to move the x across to the other side of the equation by doing an inverse of the x. So that is the inverse of the fundamental matrix times b. That's equal to u prime. And so what's left to do if I want to solve for u? Take the integral of both sides, right? And now I'm writing down the second equation that you need to learn from this section, which is the formula for u, and it is the integral of the inverse of the fundamental matrix times b. That's it. So I'm going to come in here and do a quick little highlighting. This is the first equation you need to know. Anybody bored yet? And then this is the second one. I'll go a little faster here. Sort of. Okay. That's it. So guys, how do you do step 2? To find a particular solution, you're going to do this. You're going to build your fundamental matrix and multiply it by u. What's u? It's right there. You take the inverse of the fundamental matrix times b and integrate it. That's the whole thing. All I have to do now, guys, is do an example. I'm going to show you an example and then we're good to go, I think. Is everybody okay? Questions? Okay, let's try an example. I guess I'll set up the example here and then I'll start solving it on the other board. The reason I like these problems, guys, is it uses absolutely everything. Almost everything from the semester is showing up in this problem. So you'll see that as we go along. Find the general solution. To x prime equals ax plus b, where A is going to be the matrix 2, -1, -1, 2. And the B vector is going to be 0 and 4e to the t. So let's take that. That's my non-homogeneous linear system of equations. Okay. So we have 3 steps to go through. I just outlined how step 2 works, but we can't do step 2 until we do step 1 first. So let's just, the sooner I crank this out, the sooner we'll be done. Let's just do it. So for the solution, I'm going to start off with step 1. Now on step 1, remember for step 1, we ignore the b completely. And we're back to just this good old linear system. And by the way, I already promised you I will put one of these on next week's test. I will also promise you that it will be only a 2x2. And that's because actually finding the inverse of a 3x3 matrix, we did learn how to do that, but not for a matrix that's filled with functions inside of it. Keep in mind, capital X, right? It is a matrix of functions. So doing a 3x3 inverse by hand of a matrix of functions would be really an onerous task to ask you to do. If it was all filled with just numbers, maybe it's okay, but not so much for a matrix of functions. So I decided, I think I still left one in the review packet for the final, but you could just ignore it. Basically, you want to focus on 2x2s, just like this one here. Okay, so the first step, as you guys know, is to find the eigenvalues and eigenvectors of A. I'm going to do that first. So we're going to do the determinant of, what is it, 2 minus lambda, and then -1, and then -1, and then 2 minus lambda. And if I work this out, I'm gonna get 2 minus lambda squared and then a -1 on the end of it. Okay? Let me go ahead and multiply this out. It's lambda squared minus 4 lambda plus 3. And that factors nicely. It's lambda minus 3 times lambda minus 1. And as usual, we're going to set that equal to 0. And so I get lambda equals 3 and lambda equals 1. So there's no repeats. And I actually know already that this is not defective. Not defective because there's no repeats here. Now I just have to find the corresponding eigenvectors. I have 2 different lambdas to work with. I want to be consistent with my notes here, so I'm doing it in the same order. Let me just start with lambda equals 3. Okay, I'm gonna go pretty fast on this, guys. So just maybe you don't even need to take all these notes if you're feeling good. This is a pretty easy one. If I just subtract 3 from the main diagonal of A, I just get the null space of the matrix that is all -1s. And I'll cross off the bottom row, and I'll circle my pivot here, and I'll let y equal t, and then x is going to equal -t. Basically, you're just going to get that. And so your eigenvector here is -1 and 1. And so what's your first solution? Your x1 of t? Well, it's e to the 3t times the vector -1, 1. I'll go ahead and circle that one like so. Okay? So that is that. The other eigenvalue is lambda equals 1. Let's do our null space again. So this will be a null space. Same kind of thing. I have to subtract 1 from the main diagonal over there. Then I'll get a 1 and a -1, and then a -1 and a 1. Again, I'm going to go quickly. I'm going to cross off row 2. And I'm just going to bust out my eigenvector here directly. As you can see, if I just look at this equation, x minus y equals 0. So x and y are equal. They can both be equal to t, and then you bust that out, you'll get 1. Doing that pretty fast. But then my second solution, x2 of t, becomes e to the t times 1 and 1. That's x2. And so finally, my complementary function, this is the end of step 1 now, is to just write down the complementary function, which would be, as you guys know, c1 times the first solution. I'll actually write it out, e to the 3t times -1 and 1, plus c2 times e to the t times the vector 1 and 1. And I would recommend putting a box around that so that you can refer back to it easily later on when you get ready to go to the general solution. Okay. Any questions so far? And if I am going too fast, you should slow me down. Yeah, Edgar? It could actually be defective. I think actually it could be because it wouldn't be defective with complex numbers because that would require a 4x4 matrix or larger. But if I had gotten the same eigenvalue twice, it could have been defective, and we might have had to do that whole W thing from the arcs with the W's. We could potentially have to do that, but it would only be on a 2x2. So you wouldn't have to worry about all those different cases like super defective, mixed eigenvalue, all that. It would just be a basic little 2x2. But yeah, it could be defective. That's a good point. This one, however, is not. And I've got my complementary function good to go. I'm trying my best not to erase the stuff that I'm going to need as I go along. I think we should write down the fundamental matrix next because we have everything we need for that. The fundamental matrix is just built with columns that are these x's that we solved for, the x1 and the x2. So let's see if we can do that, guys. So I'll actually call this step 2. We can kind of think that we're starting now onto step 2. The fundamental matrix, you're going to see me draw it as a giant big capital X. That is a matrix whose first column is the first solution over here. Now, let me just be clear about this. The e to the 3t actually is a scalar that can be put inside the column of that vector. And so if you were to do that, the first column would be negative e to the 3t, e to the 3t. Okay, so that's how it actually would look. And then the second column, I would take this e to the t and shove it inside the two slots there, and I would just get e to the t, e to the t. So that's your fundamental matrix. So far, so good? Now we know what the particular solution is supposed to be. It is supposed to be the fundamental matrix times u. However, I don't know what u is yet, so I have to go over and do this part of it first. To figure out what u is, guys, you have to take the inverse of the fundamental matrix times b. Notice that we have not even used this b yet, right? This b hasn't shown up in anything we've done so far. That's coming later, right? But I have to take x inverse times b and then integrate that. The thing that's, I think, the hardest about this section is just that it's a long bunch of steps. I write this down, then I got to take the inverse of it, then I got to multiply it by b, then I got to do the integral, then I got to multiply that by the x again. So you just, that's why I want you to do 3 or 4 of these to make sure that you are with it. But no individual step is really that hard. Now, the inverse of a 2 by 2, and this is wonderful review for next week. I'm going to write it over here, guys. Sorry to make some of you turn around. But this is one that we learned a ways back when, right? So the inverse of, sorry, James, inverse of ABCD, if you remember, is 1 over AD minus BC times, swap the diagonals and put minus signs on the other two. So that's a good thing to have down kind of cold so that we can use it. I'm going to use it right now, right here. So I'm going to get the x inverse. Yeah, so it's 1 over AD minus BC. So guys, what is AD minus BC here? E to the 3t times e to the t is actually e to the 4t. There's a minus here. So minus e to the 4t and then minus e to the 4t again is actually minus 2 factors of e to the 4t. Okay? And that's my AD minus BC. And then within the matrix itself, I have to swap the diagonals. And I have to put minus signs on the off diagonals. And there's my x inverse. Okay. Pretty clear on that? So AD minus BC goes on the bottom out in front as a scalar, reciprocal on the bottom of the front here. And then the matrix entries just have to be tweaked according to my little 2 by 2 inverse formula. We did that way back when. That was like February, long time ago. Now, some people wonder, do I need to multiply the scalar into the slots of the matrix here? You can, but you don't have to. And I actually prefer to kind of leave it out in front so it's not getting in my way, because the next thing I have to do, guys, is I have to multiply this inverse matrix by the b vector. So I'm going to write it down again here, guys. Basically, it's 1 over negative 2 e to the 4t times, I'm just recopying the same matrix again. Same matrix again right here. But this time, I'm going to tack on the b vector. I'm going to multiply this by the b vector. Okay? And to do that calculation, I can leave the scalar here in front. I don't have to mess around with that. I can just leave it the way it is. I'm just going to do this matrix multiplication here, guys. I'm going to go across the rows of the inverse matrix and down the column of B. As I do that, for the first entry, I have 0 and then minus, so let's just get this going here. I have a minus 4e to the 2t. Okay, that's on top. And if I go across the bottom, I have 0 minus 4e to the 4t. So it looks like that. Now, you will want to clean this up if you can, because the next thing you're going to be doing is the integral of that. So you're about to integrate this thing, and I don't want to integrate it if I've got t's inside and outside the matrix. Let's clean this up. I think you can see that if I shove this scalar into the individual slots, I'll cancel the minus signs. The 2 will cancel with the 4s, and I can combine the exponentials as well. Let's get that all nicely tidied up. So I'm going to come here and write one more line, guys. I'm going to get rid of the minus signs. The 4 divided by 2 is just 2. And e to the 2t divided by e to the 4t is actually e to the negative 2t. Okay? The bottom slot is even easier because I have e to the 4t being divided by e to the 4t, and that cancels completely, and all that I'm left with is the 4 over 2, which is just 2. So that is the answer. Okay, I'm going to have to erase this incredibly important equation. I'm going to recopy it right here. I won't put a whole million stars around it again, but that's the equation, because I need more room. Any questions so far, guys? What is this that I have in front of me? It's x inverse times b. The reason I have it is because to solve for u, I have to integrate x inverse times b. That's the next thing I'm going to do. So for u, I'm going to do the integral of, so this is an equation that's new from today, guys. We have to learn this one. One of the 2 equations we definitely need to know. I'm going to integrate this. So this is the integral of whatever we just wrote down for x inverse times b, which is 2e to the negative 2t on top and a 2 on the bottom. So we're going to do the integral of that vector. And when we do that, my friends, we integrate just entry by entry. So you just have to be able to integrate the 2 entries here. If I integrate e to the negative 2t, if I integrate it, a factor of negative 2 goes on the bottom, right? So the antiderivative of this would be e to the negative 2t over negative 2. The over negative 2 part cancels with this 2 and just leaves you with a minus. So it's just minus e to the negative 2t. And the antiderivative of 2 would be 2t. Exactly. I always get the question, do I need to add plus c? In this moment, normally when you do antiderivatives, they always harp on that. But remember, guys, we're only looking for one particular solution. We do not have to find every potential antiderivative here. So we might as well choose our plus c to be 0 so that we don't have to deal with it. And this is fine. So you can just not worry about the plus c in this particular context. And guys, I have solved for you. The last thing I have to do now, if you're still with me, is write down the particular solution. It is simply x times u. So let's write that down. X sub p is x times u. Now, x should be somewhere on the board. It's right there at the top of step 2. I'm going to have to recopy it again. Negative e to the 3t and e to the t, and then e to the 3t and e to the t. That's x, and I'm multiplying that by the u that I just wrote down, which is right here. And what do I have? What I have is a 2 by 2 matrix multiplied by a single column here. And I can just do this by matrix multiplication, right? So the first entry, when I work this out, is, let's see, e to the 3t times e to the negative 2t is e to the t. and the minus signs are canceling. And then plus 2t e to the t. Right, 2t e to the t. On the bottom row, I have e to the 3t with a negative e to the negative 2t. That's going to be minus e to the t. And then the bottom right corner is 2t e to the t. We're just doing matrix multiplication here, guys, but it has functions in it. It's not just nice numbers right now. These are actually functions. But this is your particular solution. That's it. That's the particular solution. And so, last but not least, we have to write down step 3, which, as you know, is pretty much a rubber stamp. We have the complementary function. We have the particular solution. So I bet you can write down step 3 even faster than I can. Let's try it. So step 3 is where we write down the final answer for x of t. It is simply, I'm actually going to write it out. Remember, I told you that if you want, you can just write x of c of t plus x of p of t. Like, in other words, I would accept this as an answer just because it saves you some time having to recopy it. But I'm going to go ahead and fill it in. So c1 e to the 3t times negative 1 and 1 plus c2 e to the t times 1 and 1, and then plus the particular solution, which is this guy, e to the t plus 2t e to the t, and negative e to the t plus 2t e to the t. Final answer. What do you think? How's that look to everybody? This is how you do non-homogeneous linear systems of differential equations. You just do step 1 just like before. We have this little process we learned today for how to do step 2, which involves 2 equations that you need to learn, this one and this one, right? Those 2 equations will allow you to write down x of p, and then finally you add them together, like we always do. That's it. Doable? Very. I just have to make sure the integrals work out okay. Yeah, as long as the integrals work out right here, you do have to be able to do this integral, but other than that, yeah, it's just I don't want to make this sound too easy because I've seen people struggle with it. Mainly when people are struggling with it, it's just because it's kind of a long methodical thing that, you know, if you aren't really focused, you can kind of lose track of, what do I need to do next? And then next after that, and then next after that. It's kind of like boom, 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 one thing after the next after the next. But that's the whole thing. And we have made it to the last page of my notes. Yes. Finally, right? Like nothing else to say about it. So, okay. Questions? Yeah, it is a nice review of a ton of stuff, guys. Chapter 7 is right here at the beginning of it, right? Then you're writing down a general solution. That's kind of using the idea of a basis and having a spanning set. Then you gotta take an inverse of a matrix. That's chapter 2. You've got to do matrix multiplication, which is chapter 2. Yeah, there's just a lot of stuff here. It's a lot of stuff. Maybe not every single chapter, but there's a lot. There's a lot, no doubt about it. The idea, the 3-step process, that big overarching idea, is something we also have learned before, and we're bringing that back to the surface here as well. So I think that's kind of the idea. Okay, if there's no questions, I will erase this, and we're going to spend the rest of today kind of getting ready for what's going to happen next week. So I'm going to give myself some room here to write a few things down. So yeah, let's talk about the final that's coming up next week and kind of where things stand. So the final exam for this class You have two choices. You can take it on Tuesday or you can take it on Thursday if you're free on Thursday. I don't know if everybody's always free on Thursday, but you have the choice. As far as I'm concerned, you can take it on Tuesday, the 13th, or Thursday, the 15th. It's kind of your choice. You don't have to tell me in advance when you're gonna come in. It will be at 5 o'clock both days. So yeah, we normally meet at 4, so it's a little hour later. I'm going to let you work past 7 o'clock for sure, if you want to. So maybe that would affect your decision as well. I'm not sure, but I've at least reserved the room until 8. But you know, I'm not writing the exam so that everybody's gonna need all 3 hours necessarily, but I'm gonna give you that extra time. So you can have a little bit of a cushion. And I'll do the exact same thing both days. So it's your choice as to, our official time for this class is on Tuesday. But if you think that you'd rather do it on Thursday, you can. It's really doesn't matter to me. In addition, let me write down my office hours, and I'm gonna recommend that you take a picture of this because I don't think I wrote it down anywhere. This is gonna be a lot of extra office hours. It's gonna be not my normal office hours. I'm not going hiking this weekend. I am staying put. I am every single day. Really between now and next week, guys, this is my big thing. Like I'm here. Like, I'm not here because I have family here. I'm not here because I have a house I go home to and like spruce up my gardens and stuff like that. I am here because I love teaching. And my number one priority in the next week is to get all of you guys as ready as possible for this test. I want everybody to do well and anything I can do to help. So we are gonna do a couple of things. One is I'm gonna have some extra office hours. So I'm gonna write these all down, okay? So today, you know that I'm around today, starting at 8 o'clock until midnight. But I'm going to have office hours every single day. So Friday from 7 to 10. I am kind of a night owl, so you can come in Zoom or in person. It does not matter. Saturday from 7 to 10. I want to point out also on Saturday is the day that that last little homework is due. There's just 2 problems on it. You could probably go home and do it today within an hour if you just want to get it done with. But that homework will be due. It's just practicing this method twice, just to make sure you got it down. Sunday also from 7 to 10. So all 3 days, Friday, Saturday, Sunday evening, I'll be around most of the night. On Monday, I'm gonna start doing some morning stuff as well. So starting at 9 a.m. until noon. And then again in the evening as well, from 9 until midnight. And then on Tuesday, starting at 10 a.m. until 1 p.m. And then also, I guess I have to give another final that day, but I'll come back from 4 to 5 at least, just right before the final. I'll be here as well. So I'm gonna have all of those hours. I actually haven't thought quite yet about Wednesday. And so for those of you who might wait till Thursday, I don't know. On Wednesday, I'm gonna have a whole bunch of grading to do by then. And I will probably want to get that going. So I will be checking in about any later office hours later on. So that's the first thing. The second thing is that I have decided that I am going to run a couple of review sessions, actually myself, live. I didn't do that for the midterms, and I'm, you know, I had those videos for people to watch, and I don't know how many people really watched those or not, but at least based on this most recent midterm, which I really was not all that happy with the results of, I think I want to try and step up my game a little bit here. Yeah, I really do want everybody to do well. So if I can do anything, of course, all of this is optional and it's just me wanting to do the best that I possibly can. So I am going to do these review sessions. Now, let me just explain that I'm not expecting you to come. It's not an expectation. I'm going to record them on a video. I will email you the video of it. So if you can't make it in, it's okay. You can just watch the video, or you can just ignore it completely and say, I'm going to do my own thing. That's totally fine. Or you can come in person, and I'm going to do them in this room. I know that Sunday is Mother's Day, and I'm very sorry about that. This happens every year. That I end up with this being the final sign, but I'm gonna do a Sunday review session in the afternoon, starting at 4 o'clock. You can see that's why part of why I'm not having office hours on Sunday until in the evening. And then I'm gonna do another one on Monday, which will be in the evening, between 7 and 9. And I will be bringing mostly practice problems to work on. In a minute, I'm gonna pull up my Canvas page and show you that I already have review session video that I've done in the past, and you may feel that you just wanna look at that, which will be totally fine. Yes?
Will both days have the same problems or different?
I'm gonna try and do different problems, but I'm also gonna try to have good coverage, so I will be cycling through as much stuff as I can on Sunday and then coming back to those topics on Monday, but with different problems. That's gonna be my idea, okay? So if you aren't happy with where you are standing right now and you think, what can I do to maybe get myself in better shape this time around, I'm at least gonna do my end of trying to help make that happen by doing a couple of review sessions here. So that is that. Okay, any questions so far?
Yes.
Please.
Is there any extra credit opportunities coming up?
For the final. So I once upon a time tried to do that. I tried to, like, during finals week, have people do some sort of extra work outside. And what ended up happening is I found out that there is some kind of policy that I'm not allowed to assign. I don't know, somebody complained or whatever, I don't know. So there's some kind of a policy, I'm not supposed to assign like stuff to be due like during finals week, because people are supposed to be home studying. But technically, I guess technically finals week doesn't start till Monday morning at 7 o'clock. Let me think about it. So that kind of brings me to what I want to do next, which is I want to talk about this exam that we just took and passed back your exams. Normally, I do not go over exams in class, but I am going to say a few words about this particular one. I don't know what, something kind of weird has been going on, which is that you guys actually are much more active than my other section in terms of like coming to class, being engaged, going to office hours, all of this stuff. But for whatever reason, I don't know if you guys are like slipping all the answers to them like in 10 minutes before they come in here. But the average in my 6 o'clock class is almost 10% higher than this class. They're taking the same exact exam. I don't know what it is, because actually you guys are more responsive overall. And so maybe they're just quietly understanding everything and never say anything. I don't know what it is. But there were 33 people in this section that took this midterm, and the average was only 54%. It was actually the lowest of the three exams, kind of then tapering down a little bit. And the median was 59. I always look at the median because there's always 3 or 4 people who get like, I shouldn't laugh about this. There are 3 or 4 people who will get like 10%. There's a few people who just are barely even have a pulse in the class, and I haven't hardly seen them for a while. And that tends to really drag down the average. So the median is really a better indicator. So the median was close to 60%. Technically, that's not even quite passing. So I just wasn't all that happy about the results of this. So I barely had a chance to digest it myself. I finished grading last night at about 1 in the morning. But I am thinking about what I might be able to do to kind of compensate this. I don't want this to be like a bad experience for people. So I need to think about what I could do. I don't have a lot of a time window to do it in. So bear with me. I will figure it out and probably send you some kind of a note about it. In the meantime, I'm going to pass back your exams now, and then I want to talk about them a little bit. So Jesus and Anthony and Omar and Elijah and Vaughn. And James. Marissa. Zach. Eric. Is Eric here? I think I saw Eric. Nathan. Yeah. Alex here. Joe.
No. Oh, yeah, that
Joe is here. Oh, Andy is not here. Nathaniel. Stefan is not here. Daniel.
Yeah.
Antonio.
Yeah, I just think that was. gonna be a-
Here is Steven here.
I think that was like,
Edgar. Angelica. Yeah. Brighton. Vinny. Is Sandy here? Sandy. We're both here. Gwen. Did anybody not get their paper back? Let you look at that for a second. I'm going to pull up my Canvas page real quick. Okay, let me pull the screen down.
Like we have to choose for them.
All right. So guys, as I mentioned, in the third midterm resources folder, I did post the solutions to this exam. I'm gonna pull them up here for a moment. I don't normally go over exams during class because I feel that, well, I've got the solutions here and people can just look at that. And also, some people don't really need me to go over all this stuff in class, but I would like to point a couple of things out specifically about it. This first problem, for the most part, was fun. Actually, it was really quite good. This was almost the same as the one that was on the extra credit quiz. So maybe that's what I need to be doing. Just kind of getting prepped up with the quiz problem, because this one works just like that. And it's a 3x3 matrix. I gave you the eigenvalues. Almost everybody got the eigenvalues right, the eigenvectors right. A couple of people just didn't quite get the matrix, or some people just didn't read the directions that you were supposed to write down S and D. And unfortunately, that was part of what you were supposed to do here. So that was the biggest problem there. Part B was really just writing it down. Once you have found the eigenvectors and eigenvalues, you don't need to show any more work. You can go straight to the final answer here. It's just a non-defective 3x3 linear system. And you can literally just put those eigenvectors into these terms and with the appropriate exponentials in front. So e to the 3t, e to the 3t, and then 0, basically e to the 0, which is 1. So that page, a lot of people heard. It was really, really no problem. On the second page is where things got a little more interesting. I know this might be a little bit hard to read, but again, these solutions are posted up in Canvas. So I said, suppose that we have a transformation from P3 of R to R5 that is linear. And then I gave you T of these 4 polynomials here. So I gave you T of x cubed, and I gave you T of x cubed plus x squared, and I gave you T of 2 plus x, and I gave you T of 4 plus 3x. Actually, One thing I want to remind you guys about the range of t, because question A is saying find a basis for the range of t. So I do want to remind you about this because very few people took full advantage of what you can do here. The range of t is the span of the transformation. You just make a list of all of the transformed basis vectors for V, but this is where V1 and V2 and dot up to Vn is any basis for V. Any basis. A lot of people clearly spend a lot of time trying to figure out, well, what is T of X? And what is T of X squared? And what is T of 1? And that's not wrong. Like, you can do all of that and get those results and then use that. But you don't need to do that because, guys, I actually already gave you a basis for P3 of R. It may not be the standard basis. But if you take X cubed and you take X cubed plus X squared, and then you take 2 plus X, and then you take 4 plus 3X, guess what? Those 4 polynomials, they are a basis for P3 of R. And you're allowed to find the range of T as the span of the transformation of any basis, which just means that you don't have to do any extra work. You can just say, oh, well, then it's the span of what was given to me right away in the problem, right? So you can immediately just use those values, right? So you can use, let me get the numbers here. You can just take it as the span of -2, 1, 0, 1, 4. And then the next one that I gave you was -9, 6, 1, 9, 10. You don't have to edit that. You can just live with exactly what was given here. And this is no problem at all. Like I said, some people put a lot of effort into replacing these 4 vectors with what would have been T of 1, T of X squared, and T of X cubed. And that's not wrong. That would just mean you had 4 other vectors here. Right? Edgar.
How would we have identified the ones that you gave us as bases?
If you look at these, so how do you know this is a basis? So here they are. 3, say the other one, 4 plus 3x. It's a good question. Technically, you have to check that. But I can see, for example, that X cubed is a pretty standard basis vector. And if I subtract these two, I can get X squared. Right? So I've got X cubed, I've got X squared. And then down here, I see that I have, like, I could make a combination of this and figure out how to make X out of it. And I could figure out how to make 1 out of it. So you can get 1, X squared, and X cubed as a combination of those 4. Which means that these 4 are going to span P3 of R. And there's 4 vectors. P3 of R is 4-dimensional. So the dimension matches, right? And I mean, you can also just check if these are Li. If you remember how to do that. Remember how to check Li? We put our vectors into the columns of a matrix and then augment it with zeros and do EROs. So that's actually what you need to do here. A lot of people did not. A lot of people just figured out their 4 vectors and said, that's my answer. But technically, you have to check these. And by the way, notice that I'm putting them into the columns. They look like rows on paper. But when I'm doing my Li check, they should be written, or I guess transposed into columns. Right? And then for the Li check, we always augment here with zeros. This was a little annoying. I am going to admit to you that you saw in my solutions, if you looked at them, that I had to do about 3 or 4, maybe even 5 EROs on this. But the fact of the matter is that these 4 vectors are not Li. They're not. When you do the EROs, you will only get pivots in the first 3 columns if you check my solutions, which actually means that the 4th vector there should have been removed. Should have been removed, so a lot of people didn't do this at all. They did not check the LI piece, and so it was hard to give a lot of partial credit on that. I did give people credit if they. So if they set up this matrix and then you did all the EROs and made a mistake and ended up with pivots in all the columns and told me they were a basis, I would have given you almost full credit for that, because it means the only thing you did wrong was actually just some kind of a quirky ERO step, which would have been an easy mistake to make. So I was tried to be nice about that. But if I never saw this matrix anywhere on the paper, then that wasn't so good, because like, okay, the person doesn't realize that they need to check that this is a linearly independent set in order to be a basis. Am I talking too fast here, or are you guys with me? Make some sense? Yeah, so that takes us back all the way to kind of how we did things in chapter 4. It's this stuff just ties together so much. Now, the second part of this question, there's another piece to it down here, which is to decide whether T is 1-to-1, onto, both, or neither. I took your answer from part A, and if you said that these 4 vectors were a basis for the range, I took that as your information to do part B. And if you had said that all 4 of these were a basis, then your answer to part B would have been 1-to-1. And I gave full credit for that if you gave me the justification. But the problem with part B was a lot of people didn't write very much down. They did not write down, for example, the general rank nullity theorem. That absolutely needed to be there, right? And this was a big deal, right? We've used this so many times. The dimension of B is the dimension of the kernel plus the dimension of the range. And absolutely have to, if you're gonna tell me whether T is 1-to-1 or not, you have to know something about the kernel. Because, and by the way, some people had that backwards. Some people were mixing up the kernel with the range, but on terms of 1-to-1. 1-to-1, guys, that means the kernel is 0. Onto means that the range, and I know this was before spring break, so it was a little bit of an older topic that you had to go back and definitely review. But it wasn't just one person. There was a group of people that didn't have this down. And also didn't give me this. And it's very hard to see how anybody's gonna get a lot of credit for understanding this question without knowing at least this stuff right here. Okay, so you can figure out that the dimension of T3 of R is 4. This is the number you don't really know, because you didn't do, in part A, you were working on the range. And so then it just comes down to this. The correct answer was that this was supposed to be a 3, which would make this a 1. If this is a 1, then that's a no on the 1-to-1. As I said, some people made a mistake and got 4 for this number. And then they got 0 here and told me it was 1-to-1. But again, I tried to be gentle about that if that happened. So anyway, so this question, I know it's only a 5-point thing here, but this could have gone a lot better if people would just sort of write down the general rank nullity theorem on their paper. Get the definitions here. Like some people were just sort of writing like something like that was written in some random place, but with no context. I didn't know, well, so you know the kernel's not 0. What's that tell me? You have to spell it out. Oh, that means that T is not 1-to-1. A couple extra words will really get you a lot of mileage on that. So this particular problem definitely hurt some people, especially part B in terms of the concept behind it there. But if you review the solutions here, you can kind of see what I was after. Okay, let me go on. Number 3. Oh, this really broke my heart a little bit, I have to say. There was one just like this in the all caps sample test. Just like it, almost exactly like it. And so I gave you a non-constant coefficient operator L, and I said find all real numbers R such that x to the R is in the kernel of L. So this is not a constant coefficient differential equation, guys. And that means that you cannot use the e to the rx. This e to the rx, the way you form those solutions, that works great if it's a constant coefficient differential equation, which is coming later in the exam. But on this problem, it's not constant coefficient. I see an x squared as a coefficient. I see a 4x as a coefficient. And I specifically gave you the trial solution because technically we didn't really focus on these differential equations, so I have to tell you what to do. And I did. I said, don't use that, use this, right? So use x to the r as your y of x. Now, what you have to do, guys, is you have to take, you can see there's a d squared here. You're gonna need to take two derivatives of this. I'm happy to report that that went quite well. So people know how to do the power rule on this, right? So you have to take two derivatives of this and then plug it into your left hand, plug it into your L basically. Right, so you're gonna take L of y. And the L is given, it's x squared d squared plus 4xd minus 10 and of y. And again, like I said, if you had never had one of those presented before, I might be a little okay with this being kind of weird because you are not used to working with x to the r. But like I said, there's nothing different about this than some of the ones we've seen before. And I know that there was at least one homework problem as well where we were using this kind of a format. So you just have to plug everything in and set it equal to 0. And once you do that, you can solve for r pretty quickly. The details of the calculation are here. You get a quadratic equation that factored really nicely. So you get two values of r, which are -5 and 2. And that's all that's being asked for in part A. It went reasonably well. A lot of people got that right. But just to reiterate again that this is not a problem coming out of the blue that was never shown anywhere before. The second part of it is to write down a basis. Second part just wants you to write down a basis for the solutions, and of course that's just, take the two values of r that you found and make two solutions out of them. So x to the -5 and x to the square. That's it. You were asked to check that they were Li, and that was kind of a tip off. A lot of people recognize that as well, that you have to do a Wronskian for that. So you do this W test, and that gives you a non-zero Wronskian. So they are Li, and that means they are a basis, x to the -5 and x squared. Again, not too bad on that part. But what really got me actually was this, which was worth 9 points. And I can't believe how many blank papers I saw that people just totally punted on it. And again, this is not something that you have not seen before. So the thing here is, okay, we look at this thing and we say, do we have an annihilator? So this is a non-homogeneous differential equation. So the right-hand side is not 0, it's the square root of x. Do we have an annihilator for that? Okay, there were some people who tried to tell me that the annihilator of that was d to the 3/2. Okay, if you can tell me how to take 1.5 derivatives of something, I will be more than happy to let you use this operator to work on your differential equation. I don't know how to do it, but maybe you do. No, it's not in your table. If you look at that annihilator table, the very first item says, if I want to annihilate x to the k, I can use d to the k plus 1. But that would not make sense for a value of k that was like a fraction. So if k was like 1/2 or 1/3 or something like that, it wouldn't make sense. So this really cannot be done with annihilators. Another reason that you might suspect that you should use variation of parameters method is it was nowhere else in the test. And so if I'm gonna ask you about it, this is it, because the rest of the exam is other stuff. But yeah, this is done with variation of parameters. And there was some folks that did kind of work out the U1 and the U2. I gave as much credit as I could for that. Very few people, though, probably 10% or less, actually came up with the particular solution down here at the bottom. So it was a bit of a struggle, to say the least, on this particular one. The first step is you got to figure out that it's variation parameters. And then once you do that, anybody who used variation of parameters had the formulas right, and they were trying to plug away at it. But these integrals are actually not bad because they're just powers of x here. And so I don't know, in some cases, just minor calculation mistakes that just kind of mess things up. It wasn't a big deal to me at that point. But yeah, I would have liked to have seen less totally blank papers on this particular one. So I'm taking notes on this as well, okay, need to see if people can do this variation of parameters method. Number 4 was great. Nothing bad to say here. This went fine. This was an annihilators problem. A few people didn't quite solve for the A, B, and C correctly. I only took off a couple of points if you didn't even try. If you tried to solve for A, B, and C and you mostly got it right, I would have maybe only taken off 1 point out of the whole problem. So that one, I don't have a lot to say about. I think people have seen that plenty. 4B, same thing. This one went pretty well. When people lost points on problem 4B, it was usually just something silly like, oh, they forgot to write down one of the roots, or they just, well, there was one thing I should mention. This +5 on the end here, that actually has an annihilator of D. And a lot of people did leave that D off. There is a root R equals 0 here. And so you do have an extra term in the particular solution that is associated with the root 0. That was missing from a lot of papers. So just a small point, when you're looking at the right-hand side of your differential equation and you're looking at what's the annihilator of it, you have to take each term and find the annihilator of each individual term, right? So that's an important thing as well. Okay, so, but nobody was totally not getting how to do that problem. That went pretty well. Problems 5 and 6, okay. Problem 5 was the one that you had to do the Floy process on, because it had some imaginary eigenvalues, and almost everybody got the eigenvalues right. But then, you have to do this whole null space stuff. One of the eigenvalues was real, and the eigenvector for that, it's a little messy actually, but most people did okay with that. That wasn't a big problem. It has a little bit of fractions in it. But I think some of you guys maybe should go back and review this Floy method one more time. Okay, because, and not only the Floy method, but just how you get your eigenvector for this imaginary root. So we have -2 + 3i. And how do you find an eigenvector in that case? So you see, you get a matrix here that looks a little messy, but one thing for sure, you don't want to cross off the row that has all these nice zeros in it. So you know that you're going to be crossing off a row. Don't cross off the row that has all the nice zeros in it. Cross off one of the bad rows. Okay, so you can cross off the middle row, because that nice row on the bottom actually allows you to very quickly write down that C is equal to 0. Okay, and once C is equal to 0, then you can do the AB trick with the X and Y coefficients of the row that you did not cross off. Guys, I'm just kind of going over this quickly right now, but if anything I'm saying is oh, I don't know if I could do that, I really encourage you to come in, because there's a good chance that I may ask about this again, especially because I'm not sure everybody's quite got this down. You have to remember that AB trick. You take these two numbers, you swap them, and put a sign change on one of them. And that's how you make your eigenvector here. And then from there, you have to do the Floy process. There were certainly a good number of people who did that just fine, and that didn't have a problem with it, but there was also a good number of people who didn't really get, down close to the final, answer here at the bottom, so I admit, it is a long process, this is a 12-point problem, there's a lot to this, takes a full page to write it out. And so people got to various points along the way with this one. There were certainly some people who got full credit on this. But it was also a challenge, I think, for some people too. So if that's something you're not real confident in, let's go back and look at it again. We certainly did those in class. The next problem is the defective system. You probably knew one of these was coming as well. I know we just learned it last week. That makes it tough, no doubt about it. This one turns out to be in the super defective case. And so you had to get that. A lot of people got the eigenvalues right. Again, that was good. Maybe you're using those fun facts to check them. That's always what I hope. So use those fun facts to get those lambdas, but then you got to get the right case. This was a super defective one. And so for that, you had to do the whole thing with the W's, right? And I think some folks just maybe didn't have quite enough practice with that. It did come kind of right at the end last week. So just gonna encourage you to read over this solution, and if it's something you still don't feel comfortable about, for sure come ask me. If you look at the sample finals, you're gonna see Floyd, you're gonna see defective systems with these W's. There'll be more practice for you to find in there for sure. Okay, and then the last problems were kind of just these smaller point conceptual questions, and for the most part, actually, this wasn't too bad. I felt pretty good about this. The dimension of n3 of r is 9. And so if you want to have an isomorphism to Pn of r, you have to figure out what's the right n value. And it has to be the same dimension. Most people, I think, knew that and got n equals 8, which is the right answer because the dimension of P8 of r is 9. And then I asked you to write down some people didn't do both parts. So it says, what is n? And then write the isomorphism. So the n value is part of it, but then I also wanted to see the formula written down. And we had homework like this as well back in chapter 6, and you just had to write it down. It's kind of, there's only one natural answer there that could possibly work. And so I've got it there in that box for you. It's just the different powers of x with the entries from the matrix as coefficients. There'll be 9 terms there. Yeah. Problem B, part B. Some people got this. Most people did give me, you knew this was coming, right? The most important equation in chapter 7. I gave people 2 points just for writing that down, even if there was nothing else on the paper. So that was almost half credit just for writing that down. But then to actually get the full thing, you can see you have to figure out what is a squared times b. So that takes a little bit of a calculation. I was happy to say I saw very few people do this. And so I don't want to give anybody any ideas. You cannot do this, right? Because this is a vector times a vector, which makes no sense, right? With vectors, we can do what? Addition and scalar multiplication. We can't multiply vectors in. So I was glad to not see that. And instead, what a lot of people did is they got it right. They said, oh, let's figure out a squared times b. And then you kind of work it out the way I showed it there. So anyway, this one, if you go back to the review session for the third midterm, I have one just like that in that review session. I'm not sure if everybody looked at that or not, but that was kind of what was involved there. The last part, it says, what is the value of d that turns this into a circle? So I'll tell you, first of all, I gave people half credit if they just told me that if all they wrote was, oh, it needs to be plus or minus bi for the eigenvalues, that was worth, I guess, 2 points out of 5, just for writing that down. And so then you actually have to write down this characteristic equation, and I gave people a point or 2 just for writing that down as well. The actual quadratic formula is a little messy. when you do the, the negative b plus or minus, the square root of b squared minus 4ac, this thing that you see down here in the solution. It's a little messy, but then you just have to figure out, well, how does that turn into just a purely imaginary number with nothing in front of it, no a value here. And a lot of people saw through that and got that to work out. So overall, these conceptual ones, as much as I think people sometimes don't like them, I thought that they went okay, relatively okay. It was really problem 3, the one that was the variation of parameters, and maybe a little bit of the previous one on the range. Those 2 problems kind of put people kind of behind before I could get to the rest of the exam. So if you have questions about your own exam, I want to encourage you to stop by and talk to me about it. We can go over it. I can discuss with you what we could do better for the final and so on and so forth. Okay. All right. Well, why don't we take a short break? When we come back from the break, I'm going to give you a quick overview of a whole bunch of the semester. So I'll give you a chance to stretch your legs, get some fresh air, and we'll only have like 15 minutes, but I need you to come back. I want to do that quick overview and kind of wrap up the class. So I'll see you guys at about 5, just make it 5:35. We'll just have a short little wrap up.
My notes is right here.
Yeah.
Time constrained. Let's get to put a 10.
Right.
Yeah, because I knew like what to get.
Yeah.
Sorry, I thought I hit it. Not that. Oh, no, you're fine. Sorry about that.
Like I thought everybody was like that, and I think that, oh, you have some more, I'm like.
Yeah.
"Okay."
Okay.
But I don't do that, I've been working. In this area.
Okay.
Yeah, I don't know if it's like on Zoom or in person, but either way, I'm never too sure about it. It's on Zoom.
Okay. It's on course.
Yeah, it's a workshop, so I mean, I'm not gonna have to exam.
Yeah.
Yeah.
Kind of a break from the partnerships of the
Yeah.
regular monitor. Build up most of the ones.
Oh.
Are you taking another day or not?
Yeah.
I was like, I. Just do that. Five. Whole 3 hours.
Oh, right.
Gonna be at the bar.
This one.
Like,
Thursday night.
How long will be here?
Your kids.
Like, drink.
Oh, you're drinking.
Fuck that.
Just, yeah. Yeah.
I don't know, it's,
Yeah, but I think this last thing, really just strengthened a lot of the previous stuff.
yeah. We're thinking about.
Other states, this is my first.
I know, yeah. I want to see that.
Yeah.
You can bring them, you can sit in the back.
I know.
Take notes.
Yeah.
Never forget this.
My wife will be stoked.
Yeah, she'll be really happy with you.
Yeah.
That's how our Mother's Day are gonna be.
Yeah, yeah. It's like, this is my last Mother's Day.
Yeah, I am so sorry. I just, every year this happens. Like,
Yeah, that's okay.
Mother's Day is like right before finals.
I don't mind that.
Oh, yeah.
Yeah, you're probably trying to just get away from your kids. It's your Mother's Day.
I just need a break.
Yeah, it's your day, so you do whatever you want.
Yeah.
Yeah.
Yeah, it's,
Yeah, so
Whatever works.
kind of same time.
That's how Mother's Day should be. One, to be with the kids. You be with the kids. If I don't want to,
I know.
then you have a day break.
Yeah.
Yeah.
I don't know, I really look at it. It's like all holidays.
Well, I'm doing.
Yeah.
Yeah.
I don't know.
Yes, I'll do that too. Yes, so you have three ways to see it. Either come physically on
But
or you
I
can log
actually.
on to. I have to figure it out.
Might as well sell your.
I'll probably do this. And then the third way is after the fact, I'll have a see all my materials. Yeah, I'm gonna just do, like I do with this camera here. Yeah, that's what I'm gonna do. Yeah, exactly.
Yeah.
For the.
I don't know, it's my father.
For the one that we did.
Right now.
In person.
I don't know, it just depends.
Everything is both on that. Absolutely,
Yeah. Yeah. No, I didn't get this, so I didn't get this, so I tried to get the next one.
Uh-huh,
So
that's
too,
right.
but- Yeah. Yeah.
What is that?
Oh, my God, it's been out there, it's- should be-
They don't do anything like.
Well, they have their own, they know, no, they just have their own stuff, so. Traditional.
Oh,
And
okay.
their parents are Catholic, so it's like very.
I grew up Catholic.
Yeah, yeah. They just get baptized for this month, actually.
Yeah.
So I'm kind of on the Christian side, so. Yeah, cool, I'm like, do it. Yeah.
It's more like, it was more like.
It's just,
Yeah.
yeah, yeah, I mean, that's, I just don't want them all to hit, because it was on this head and driving. This. I don't want to. Like, we were here.
Oh, you're in the other class.
This is our life.
Yeah, yeah.
Yeah.
Ah, it's right here.
Yeah.
You have to. You have to.
They love it. So this is making mistake. Yes. Oh, okay, okay. Yes, even that's like a bargain. It's very transactional. Yeah, yeah.
That's why we're.
Yeah. Yeah, yeah.
But I also don't, I really don't understand.
Yeah.
I'm like, care about it. About anything.
Yeah, yeah. You know, I'm trying to see this career path, do all that. My daughter will be an engineer. I respond to that.
Yeah. Yeah. Not a big.
Team here will push their, but
One of that is like. How she's done it, she was like, oh, no, first year. Oh my God.
yeah.
So fun with me. She wants. I'm just.
Because we.
Yeah. I don't know. I know, yeah, but I was keep like a positive.
Yeah.
In front of her, especially, but now she's
Actually,
actually.
that's misogyny.
Yeah, yeah. Now she's having like. That's her, I'm like, okay. It's better, find out for you, but Yeah, I guess. I could do whatever you want.
Yeah.
That one.
Yeah.
That's a hard.
I got one when I was going, but now. I don't do it for sure. So,
Yeah.
just things change.
Yeah.
Yes. Very last. So everyone's- Everybody just like, it's good to files.
Yeah, I was like, just in case there's like 2.5.
Oh, that's crazy.
It's like,
Oh.
2 accidents.
So now, is there?
Yeah.
You'd rather just get here early. 2 hours early.
Yeah,
So let me ask you guys a question. Just get a straw poll idea about this. If I was to write a blank midterm 3 again, I wrote another one just blank and gave it out probably by tomorrow or something, and let you work on it till Sunday night, because I can't do anything during finals week, remember? I let you do it, work it out as a take-home final until Sunday night. Do you think you would do it? Depends on what I'm gonna do. Here's what I would probably do. Because I do feel that you guys can do better. I actually do really believe that this just wasn't everybody's best day overall. I would like to give you an opportunity to earn some more points back on this midterm. But of course, I had like 5 people get already 100%, so it's a little hard. So what I would probably be doing is be calibrating how many points you can get back according to what your current score was. Let me give you an example. If you got well, we'll assume 100 is the best, even though there was some people over 100. Let's assume you got a 40%. Right. So then that means that you missed 60 points, right? So what if I made the take home worth getting back 1/3 of the points that you lost on this midterm? Would you do it, do you think? And submit it by Sunday night?
So,
Now, of course, so 1/3, that's for everybody, is different. So the person who got a 40% could increase their score to 60 because they lost 60 points, they can get 20 out of 60 back. That's assuming it's perfect, right? If there's anything wrong with it, then they don't get all those points back, right? But the person who got 91 already, you know, they pretty much already proved to me they know what they're doing for the most part. There's only 9 points here. So that person might not want to do it because even if they get it perfectly right, they only get 1/3 of those points back, which would push this to 94. So whether you're going to do it or not might depend on how you already did. So does that make sense?
our score, would that be before the extra credit or?
It's with whatever your score is right now on your paper, not included. So I'm including all that extra credit in there. So it's just whatever is recorded in Canvas, that is your score. So what I'm saying is that how much extra credit this is worth depends on how you did. The better that you did on the in-class test, the less it's worth it to do for the points value. I mean, it's still worth it for studying, but it would be less worth it in terms of earning more points back. I don't like doing this because you know why? It means I have to grade a whole bunch more papers, but I really, really care about this. I want you guys to learn it as best as possible. So I'm gonna do that. It's totally optional. Again, for some of you who scored already in the 80s or 90s, if you scored over 100%, you can't get anything more, right? This is the way this works. So it's really for people who really struggle. The more you struggled on the midterm, the more it will be worth points back to your exam that you can do. But it's up to you if you're gonna do it. It's gonna take 2 hours of your time between now and Sunday night to do it. But you can view it, of course, as part of your studying for the final as well, because you're gonna reinforce what was on this exam. That sound fair? give me till tomorrow morning to write the exam. So, but by tomorrow morning, I'll send out an email and let you guys work on that. I'll also have some rules on this, right? We're not gonna go down to our best friend professor who lives down the street and say, hey, can you do this exam for me? No, you're gonna need to do it basically on your own. Okay, so I'm gonna be expecting that. Edgar,
Will you put 96? Right?
no, I'm gonna just rewrite it as if it was like the third midterm all over again.
And then submit it like it was a homework assignment?
Yeah, I'll create a Canvas assignment for it. And you just submit it into, scan your paper in like it was a homework. And then just submit it by Sunday night at midnight. Yeah. That sound fair? Reasonable? Okay, so we'll do that. I think it'll help me feel better about the averages. It'll also help you learn it a little bit better if you need it. If you did great already, and there were several people who really did very well already, then that's fine. If you don't want to take the time to do it, you don't have to. It's just totally, again, up to you. Okay, what I wanted to say, I don't have a lot of time. I passed out a group work. We're not going to do this as a group work like we traditionally do. I just wanted to say that, you know, half of this semester has been about differential equations. And if you see a differential equation handed to you, one of the things you're going to need to be able to do by next Tuesday or Thursday, whenever you're taking the final, is figure out which tool, which method out of the toolbox do I need to pull out to solve that particular problem. So I thought it might help. Some of the questions, so some of the DE questions, before we actually look at the group work, and we're only going to have a moment to look at the group work. We're not going to do it in detail. The solutions to this are fully worked out in Canvas. But just to give you the rough idea, the questions that you might want to ask yourself is, first of all, is it a single differential equation or is it a system? That's one good question. Another good question, so in other words, is it just one unknown function that you're solving for? So if it's a single differential equation, then that would be, you know, something that we would have covered either in chapter 1 or in chapter 8. But systems of differential equations is what we were studying in chapter 9. Let me give myself a little more room here. Right, so that helps like pinpoint where within the semester did we learn about that. The second big question I would probably ask about my differential equation is, what is its order? What is the order of this differential equation? That's usually what we call n. And the answer, really, the way you want to think about it is either n is 1 or n is more than 1. So your differential equation is either a first order equation or it's a higher order differential equation. Now, guys, higher order differential equations over here, this was chapter 8. This is pretty recent material. This is pretty recent. So this stuff, we learned the techniques for this already. This is where we do annihilators. So that's one of the tools. Another tool was variation of parameters. Right, we have that as well. Really the chapter 8 techniques, okay? Writing down the auxiliary equation, it's just what was on the exam, right? But this is where I think we need to spend some time before next week, because this is older material. The n equals 1 stuff was from chapter 1, and I am going to have this on the test next week. So what I'm talking about here are, does anybody remember any of these first order differential equations? There was that word shows up everywhere. Homogeneous. What was another one? Separable, Bernoulli. Bernoulli is here, and also linear, actually. Yeah, all of those are from chapter 1. So I'm going to recommend that for sure, if you come to my review session, I will certainly be reviewing these. This goes way back to the first midterm, so it's been a while. And you need to remember things like integrating factors, The Bernoulli equation, which I really like, there was one on your first midterm. The Bernoulli equations are quite a bit to remember. There's a change of variables that you have to use. And the Bernoulli equation becomes a linear one after you do that change of variables. So that's also something well worth reviewing. Homogeneous differential equations in chapter 1, we solved those with a change of variables as well. Okay, so this goes back a while. But you can see that, you know, a lot of the semester is kind of involved in what's being discussed here in these two questions. You can almost make yourself a flow chart of like, I asked this question and depending on the answer, I either go this way or I go this way. And then ask the next question, I either go this way or this way, and just make a branching tree of options for yourself. But you definitely want to review some of this. You'll see in the Canvas resources, I've got 2 sample finals. I promise you that they have lots of this stuff to review again on them, for sure. I think aside from, so if you're gonna redo this 3rd midterm, that ought to be pretty good review of this 3rd section of the class. For most of you, you need to spend some time. Let's not forget to go back to inner product spaces. So we got to remember the things like the geometry of a vector space. So if we want to know the angle between 2 vectors, or if we want to find an orthonormal basis for a inner product space. Does anybody remember how we did that? The Gram-Schmidt process. Yes, that's how you orthogonalize a set of vectors, and then you can normalize them from there, right? So that goes back a ways. Yes, Edgar.
Equations be given again on file.
Took the words right out of my mouth. Anything that ever was given to you before. I think I gave you the mixing differential equation on the first exam, along with a table of integrals. I gave you the Gram-Schmidt formulas on the 2nd test, and of course on the 3rd test, I gave you that whole table again. I will give you all of those things again. The union of everything I've given you, I will give that to you again, for sure. So the Gram-Schmidt formulas for sure. But you know, if you see something like this, like, oh, I don't even remember what this is about, that's a tip to go back to the previous, well, to the 2nd midterm, actually. Actually, if you look at my final exam review packet, you know what it basically says? It basically says, go back to the review materials for each of the 3 midterms and just review those again. If you believe it or not, guys, you have way more stuff than you're going to have time to look at. You have the exam you took, plus the 2 samples that I had given you for each of that stuff's all still there. So that's 9 midterms. Just the midterms from the first 3 parts of the class that you, in theory, could go back and just eeny, meeny, miny, mo, pick some problems and try them. And that's not even getting to the 2 sample finals. So, yeah, so there's a lot of stuff. Inner product. So I think chapter 1 and inner product spaces would be one of the rustier topics that we haven't really talked about as much lately. Yeah, there's some other things like, you know, finding the inverse of a matrix by using the adjoint method, or by using, what was the other thing? The Gauss-Jordan method. Not a bad thing to review. That goes, again, back quite a few chapters. So there are some other things to review as well. But I think chapter 1 would be really important in that chapter 5. This is chapter 5. I'm not feeling quite the pressure to go over this in detail right now, because I am going to do 4 hours of review sessions this weekend on Sunday and Monday to kind of really be able to get into this. And I think I'll have more time to go into it there. Again, all of that stuff, all of this is optional. Some of you are already ready to go, probably. I do believe that. Some of you are really on top of it. But for many of you who want to really bring your game up a little bit, there's a lot of time and a lot of practice available to you to do that. So I have one last thing I want to do. Sorry, I'm going to stop recording for a second.